Welcome to this IM learning course on engineering chemistry. Today I am going to discuss one of the important topic from module 1 of engineering chemistry syllabus, that is atomic and molecular structure. Mainly in this video I am going to explain about why atomic structures are important and how wave nature of radiation and particle nature of radiations leads to the development of atomic structure. So at first we will try to understand with some real life examples why you must learn about atomic structure, and then we will discuss about wave nature of radiation and particle nature of radiation. So let's start with a very real life examples where atomic structures plays very important role. So almost all of you wonder that why atomic structure is introduced in engineering courses, why you should know about atomic structure. But believe me, atomic structure is so important that without the understanding of its theory, it is almost impossible to progress the engineering sectors. Various engineering sectors like telecommunications, computer science, electrical and electronics engineering, civil engineering, mechanical engineering, all depends upon the basic theory of atomic structure. That's why it is very important to understand that what are the theory behind atomic structure and how it is related. So let us understand it. So all of you are quite familiar with this picture where it is a MacBook or any computer. If you just open any computer, then generally you will find this kind of motherboard which is present in almost all the computers and desktops and most of the electronic materials. Again, if you go deep into it, you will find this kind of circuit board, printed circuit board. And do you know what materials are used in this printed circuit board? It is nothing but copper. And how the copper has been chosen, how the different printed circuit boards are made. For understanding this, a basic understanding of atomic structures are highly important, because it all about electron, proton, their electronic energy, everything. So this is one example which show that atomic structures is really important for engineering. Now we will look into more familiar examples where we will try to understand how the theory, which maybe look very dull in book, which may look very boring in class, but how that theory become applied in real life. Let us take examples of a QLED TV, which is mostly very much familiar to many of you, because QLED TVs are nowadays available in the market. So what is actually there inside this QLED TV? If you just take a QLED TV and if you just try to understand its various components, one of the important components of this QLED TV are quantum dots. Now quantum dots are nothing but the very tiny nanoparticles made up of various inorganic materials. It can be cadmium sulfide, it can be titanium based compounds. So now these quantum dots, they are very small in nature, their size is almost in the nanoscale, and if you look at any QLED TV, there are billions of colors. how these different colors are there? It is because of this nanomaterial show a varieties of color within a very short or very, we can say that, smaller differences in size. For example, if you look at the 2 nanometer particles where the emitted light is can be, you can say that, little bit fade blue, whereas if you change the size to 6 nanometer, here it becomes red. So this much small size changes can bring that much whole visible spectrum, and in between you can do whatever you want. Now how this color change happens, if you wanted to know it, you have to have a proper understanding of atomic structure, a proper understanding of theory of atomic structure. For example, one of the theory that we will discuss in this course is called particle in a box theory or particle in a box model. And the particle in a box model and its solutions are one such examples which has found real life examples. And quantum dots are known as the real life particle in a box model, particle in one dimensional box model. And the size of the box or the length of the box, which we will discuss in another lecture, this is nothing but size of the quantum dots, which has nothing but a practical applications of particle in 1D box model. So this example shows that why you should understand the atomic structure, why understanding of atomic structure is so important, so that the various engineering fields can be advanced. We can give so many other examples. Let us take another one. Again, if you just take out any of the electronics devices like mobile phone, computer, and if we just go inside, if you open it, you will get this kind of we can say the chip and this kind of resistors. They are very common. Semiconductors, they are nothing but semiconductors. So semiconductors are very common. And what are they made up of? Most of the semiconductors are either silicon or silicon derivatives. And how they are made up, how their resistance, how their we can say that semiconducting properties are changed. It's all because of the properties which is known as the band gap. A proper understanding of band gap and what are the different factors that affect the band gap. If you have a clear understanding of all those things, then you can probably be able to tune up these things. So for tuning up, it is very important that you all should know the very fundamental topic of any of the engineering fields, which is atomic structure, which is a part of your engineering chemistry course. So that's the importance of knowing the atomic structure. So now I hope that now your doubt regarding why you should study this course is clear. Now we will proceed further. So one more example, telecommunications, which is very important in today's life. Do you know how this telecommunication actually work? It work based upon various principles, but one of the important principles which play an important role is quantum theory. Because the fiber optic telecommunications is only possible because of the lasers, which are nothing but developed from a quantum theory of molecules. It's purely a transitions from textbook knowledge to real life applications. So these are the few things which explains that it's very important to have a proper knowledge of atomic structure. So by now you are all set to take this course. Probably all your confusions and doubts are clear, that why you should take the engineering chemistry course, why it is important to read the module 1, that is atomic structure and molecular theory or molecular structures. So now we will try to understand two very important phenomena. one such phenomena is wave nature of radiation. Why we should understand about it? Because most of the atomic structure or whatever molecular structure we know today, it's all because of the interactions between light and matter. Thus, after studying the interactions between radiation and matter, we are able to understand many things. So it's very important, we all must know about wave, the various properties of radiation. One such properties of radiation is wave nature. There are very fundamental, we can say that phenomenon which you already understand from your +2 level, that is reflections. Then we have refraction, so this is reflection, then reflection. We have diffraction, if you just pass through a visible light through prism, then different types of color appear, the whole visible spectrum is there. So that is nothing but known as diffraction. Then interference. Interference is nothing but again a properties of radiation where some wave combine constructively, some wave combine destructively, and interference patterns are found. So all these property, reflection, refraction, diffraction and interference, they actually justified or they have been proved by wave nature of radiation. But there are few properties which cannot be explained by wave nature of radiation. One such properties are black body radiation. Actually, there are few things which initiates, which triggers the development of quantum theory, and black body radiation is one of them. It is nothing but if you hit a particular, we can say that a solid, some light emitted. For example, if you take a iron rod and if you hit it, first it will glow red. If you take a filament, if you hit it, it will first red then become white. So it's nothing but emission, light emission by heated solids. This process is known as black body radiation. But black body radiations, as per classical theory, the intensity of the radiation should increase infinitely as we increase the temperature. But it is not happened practically. Practically it was observed that intensity goes high, it becomes maximum, then falls down. This was one of the major drawbacks of classical theory, which was not able to explain this. Now black body radiation was quite surprising for many years to many scientists, because it was not explained by classical mechanics. So there are something which was missing, and the missing point was that it was first pointed out by a great scientist, Max Planck, who actually made a groundbreaking or out of the box statement that energy, like matter, is not a continuous, it is discontinuous. That is, energy is actually quantized. Energy is not a continuous. Energy comes like a, we can say that in a in one pocket then another pocket, so it is not a continuous process. Because classical physics has no limitations on the amount of energy that a system can have, but quantum physics has some laws and it sets some values that only specific amount of energy or specific set of energy a particular body can take. So that's where the groundbreaking comment was there, that or proposal that energy is discontinuous. Now if you say something, people will not believe. Definitely you need proof against it. So later on it was proved. We will discuss that. So the difference between two allowed energy of a system has a specific value, and that value is called quantum of energy. So quantum of energy, this concept was first termed by Max Planck. After that many work have been done, and finally today we got very nice subject called quantum mechanics, quantum chemistry. But it was all started with a small problem which was not solved by classical theory, that is black body radiation. And Planck has given a equations which describe that quantum of energy. We said that if h is a constant and nu, we can say that the frequency of the light, then E equals to h nu. So now, as soon as Planck has given that equation E equals to h nu, several other scientists tried to utilize this theory, that means the quantum theory. Many scientists tried to combine that if they use the energy quantization, then it is possible to solve some of the problems. Like Einstein, one of the greatest scientists we have in the past 200 years. So Einstein was that time working with photoelectric effect, that is, if you shine a surface of metal with some radiations, then electrons are ejected, and this phenomena was not able to explained we can say that properly by classical physics. So Einstein actually utilizes the Max Planck's theory, and he tried to solve this problem by considering that the radiation is not only having a wave nature, which was previously explained by various physicists. Einstein also said that it has a particle nature. That means the photons or radiations, they are nothing but energy pockets, particles containing a certain amount of energy. And Einstein also showed that electron emission from the surface is only possible when the frequency of the incident light actually exceeds a particular threshold value. For example, if you hit a particular metal surface with 700 nanometer light, let's say there is no electron ejected. But if you hit this surface with 550 nanometer, electrons are ejected. That means this light, whatever energy it has, it is not sufficient to eject the electrons. That means there are some threshold energy which has to be exceeded, then only it is possible. And again, you look at, if you hit 550 nanometer light, the electron speed is this much, 2.96 10 to the power 5 meter per second. But if you again increase the energy of the electron, actually if you decrease the wavelength, energy is increased, because energy and wavelength are inversely proportional. Wavelength increases, energy decreases. Wavelength decreases, energy increases. So 400 nanometer light means it has more energy, more frequency, and that's how we can say that the electrons, again the velocity is more. Why? Because the we can say that the kinetic energy of the electrons, it depends upon the frequency of the light. That means if the frequency of the light is more, the kinetic energy will be more. But how? It is because a certain amount of energy definitely we need for the threshold energy, that means to exceed the threshold limit, and if any energy is left, that is converted to the kinetic energy of the electron. So if total energy of the photon is E and phi is the threshold energy and half mu square is the kinetic energy of the electron, then the E equals to, you can write phi plus half mu square. So this is very famous equations which was given by Einstein, and for the explanation of photoelectric effect he received the Nobel Prize. He has not received the Nobel Prize because of E equals to mc square, but he has received the Nobel Prize because of his contribution to the photoelectric effect. So Einstein was able to explain the photoelectric effect because of the by taking out the particle nature of the radiation. So it was proved that radiation has a particle nature along with wave nature. So if radiation has a particle nature along with wave nature, so it is quite possible that the particles can also have, along with its particle nature, it might have a wave nature. So we will try to understand this point in our next video. Thank you, and be just little bit cautious while reading this atomic structure, because it will help you a lot. Just wait for the next video. Thank you.